Chapter 18, Part 3. Okay, so I just got through extolling the cortisone adventure achievement of the Woodward group at Harvard back in the late 40s and early 50s, where they used alpha reactivity to adjust the stereocenter. So let's talk about other kinds of reactivity. So if you take a ketone and treat it with bromine, you will brominate the alpha position. That does not, however, occur on the ketone. What you need to do is set up this equilibrium between the ketone and the enol, and recognizing that enols are very electron-rich enols, very electron-rich double bonds, and if you happen to have bromine in the solution, you will undergo bromination. Right, this is an electrophilic reaction. If in the absence of this oxygen, you would form a bromonium ion. And while we can't really rule that out here, the belief is that the hydroxybromonium is less stable than the alpha bromo ketone, the protonated alpha bromo ketone, and so if this actually forms, it immediately opens in that way, and then it loses a proton. So you're not brominating the ketone here, you're brominating the enol. This bromination is so fast that you can actually titrate out how much enol there is in solution, and there's very, very little at all times, right? This is an equilibrium. Whatever else is going on, this equilibrium between the ketone and the enol is a thermodynamic, it's thermodynamically set of concentrations. So you know in your book that for cyclohexanone, that actually it's 0.12, I believe that's, sorry, 1.2% of the ketone is enolized for cyclohexanone. If you have the 5-membered ring, it's even more heavily enolized. I could point out that that's probably solvent dependent, but we can, the ratio here. But there's only about 1% of this here. But as long as we are bleeding that off, you will continuously make the enol, and the rate of the brominated product will be determined by how much enol you have. And if you have acid in there, you will promote the you'll promote formation of the enol because you'll be protonating reversibly the ketone. right? You'll be making the enol faster, but the ratio will not change, right? So as you're bleeding this off, um, you're replacing it with more of the ketone, which will enolize. Okay. Now, what's the byproduct here? This is a self-promoting reaction. So every time you do this reaction, you're generating one equivalent of HBr, which is very acidic, more acidic than hydrochloric acid, of course. And so the faster this goes, the more this reacts, the faster the reaction will occur, even though you're bleeding off your starting material. An interesting component of this is to think about anyway, is basicity. Cyclohexanone and 2-bromocyclohexanone, which one is more basic, right? Which one is more easily protonated in the presence of acid? And acidity, which one is more acidic? And another way I could actually do this is say, okay, you've got alpha bromo cyclohexanone. You've got 2 protons on this side, and you've got 1 proton on this side. Which one exchanges faster? I don't know where it wouldn't have ever been done with D2O, but if you had 2-bromocyclohexanone and you treated it with OD minus, which one of these protons gets pulled off first, fastest, more easily? Well, the answer is that the proton next to the bromide is, because this is inductively withdrawing, that makes this proton more acidic. This is actually important, okay? Has consequences, and of course I wouldn't tell you about it if it wasn't important, right? Now, how about basicity? Which one of these is more basic? Well, this one again has the bromide as an electron withdrawing group. That's an inductive effect, therefore less basic. So if you're going to protonate one of these 2 ketones, it's better to protonate the cyclohexanone. What does that mean? If you are brominating under acidic conditions, cyclohexanone or any other ketone, you will enolize and brominate once, and then you could brominate again. It's interesting to think about what happens. You protonate this, and which one of these is the more stable enol. But I'm just going to say, actually, turns out that it enolizes the other way first. But the enolization is slower. Therefore, monobromination chlorination, maybe iodination, is easily achieved. If you do the bromination or chlorination under acidic conditions. If, however, you're brominating under basic conditions, it will just say sodium hydroxide. This proton becomes acidified by the presence of the bromide. So, more acidic than the starting material. And again, we're talking about the one next to the bromide. So that will enolize and or make the enolate, however you want to think about that, and give you the dibromide. And the second step here is faster, therefore monobromination under basic conditions is impossible. It not only is faster, the second step is faster, so you can't stop at the monobromination stage, but you actually get a different structure than under acidic conditions, different product. If you force the acidic reaction to go to a second halogenation. Now, I feel like I need to say this is actually probably bromination of hypobromite. And NaOCl. Sorry. Oops. That's actually bleach, and useful in organic chemistry as a chlorinating agent. If you're going to go with a basic chlorination scheme, and it also actually is a good nucleophile. The oxygen is, but that's a different story. So the difference between acidic and basic bromination, and then it gets more interesting, and we will talk about the haloform reaction, which I wish I could do for you, but I don't have iodine and acetone and test tubes and stuff like that at home. Too bad. A lot of chemists have have home labs, or in traditionally, but I used to when I was growing up. Okay. The haloform reaction, we'll also talk about the hell of a hard Zielinski reaction, though usually referred to as the Hell-Volhard Zielinski reaction. Okay, that'll be part 4.